So now we're going to take a look at the formal definition of integral, which is the way we find the exact area. So previously we were looking at like a Riemann sum to estimate the area. But this is the basic idea. If you make the rectangles smaller and smaller and smaller, or in other words, if you do more and more number of rectangles, then you will approach the exact area under the curve. Okay, so you'll get the exact area if you do more and more rectangles. So the idea is we're going to set it up to where you have a formula, which is the estimated Riemann sum area with n rectangles, and then we're going to take the limit as n goes to infinity. So here's kind of the basic idea. If I want the area between a and b of some function, then I do the limit as n goes to infinity, and this summation is I'm summing n rectangles. How do you read this? This here is the height of every rectangle, and this is the width of every rectangle. And how do you find the width of the rectangles? You say I take the interval width, b minus a, and divide it into n intervals. Okay, so delta x is b minus a, that's the width, divided by n rectangles. So that's like each rectangle. So the width of every rectangle, and the height, you just kind of remember, you say like I'm doing f of a plus I delta x. So let me kind of show you how this kind of works. Like suppose I have a function here, f of x, and I'm trying to do the area starting at from a to b here. And I'm going to draw out the rectangles. They look like this. And let's imagine that like we're doing a right-hand sum. It actually doesn't really matter which one you're doing. But let's say I'm doing a right-hand sum, right? Rectangles. And I'm doing it into n rectangles. So the width of every rectangle we're going to call delta x. Okay? The delta is just a note for difference. It's just a notation. You don't have to worry about like that. The delta doesn't really mean anything specifically. It's just the symbol we typically use. So that's the width of every rectangle. And this is the first rectangles, I equals 1. This is I equals 2. So I represents like which rectangle you're at. So this is like the first rectangle, the second, third rectangle, and the third rectangle. And basically look at what dictates what is the height of the first rectangle. It's you're doing a plus like this value here, like this x coordinate right here is a plus delta x. And this coordinate here is you start with a and you add 2 delta x's. So this value there is a plus 2 delta x. And what's the value x coordinate right there is a plus 3 delta x. So for the first rectangle, you're doing the x coordinate you're going to use for the height of the rectangle is a plus 1 delta x, a plus 2 delta x. So for the ith rectangle, like if I'm just looking at an arbitrary I rectangle, it's a plus I delta x. And that's where this kind of this inside part comes from. So f of a plus I delta x would be the height of that rectangle. Delta x is the width of the rectangle, so that tells you what the area of a single rectangle is. And this sum says I'm going to add up all the rectangles from 1 to n. Okay? So now we're going to look at some examples where we go and try to figure out this integral sum by doing the limit. Now, similar to derivatives, right? There's a limit definition for the derivative, but and it's very tedious to do the limit definition of the derivative. So we have a lot of rules that we use to do the derivatives instead of doing that limit definition. And similar thing to here, for integration, we're going to have rules that we use eventually and later, but at the beginning, we just kind of focus on the limit definition to just sort of show you, like, it's kind of tedious, kind of annoying to actually do the limit definition. We'll go through just a few examples. You honestly don't have to do them too much to do it's very tedious calculations to do by hand, the limit definition. But, I will do a few examples so you can kind of see how it works. But ultimately, at most, you need to know just how to set up the basic idea. And then in the later sections, we learn about techniques on how we can solve these integrals and find these areas without using this limit definition. Now we're going to compute the integral using the definition of the integral, i.e. set up the area as a sum of n rectangles and take the limit as n goes to infinity. Okay, so this is definition of integrals. You're not going to do too many of these, and they're a little bit tedious because they require some complicated sums to do, but let's do it. So what we would say is if I were to split 0 to 1 into n rectangles, First, I start with the width of each rectangle would be my interval width divided by the number of rectangles. So it would be 1 over n. So that's the width of each rectangle. And then the height of each rectangle, you can actually either do left-hand or right-hand sums. Actually doesn't matter in terms of taking it to the limit and doing the integral. I typically do right-hand sums. I think it's typically easier on notation. You can do I equals 1 to n. So we're going to sum how many rectangles? Well, we're going to sum up the rectangles from 1 to n. We want the height of each rectangle, and the height of each rectangle is always the starting point plus how many widths we've been over times I. Okay, so that means we start at 0 and we count how many widths we've gone over the number of i's, and we're going to use that's the height of the rectangle. And then the width of the rectangle is just delta x, like this. So in terms of delta x, I got to replace it with 1 over n. So this comes sum from I equals 1 to n. F of I times 1 over n times 1 over n. And that's the sum from I equals 1 to n. F of I over n is just cubed. So we're going to do I times 1 over n cubed times 1 over n. And this is the sum from I equals 1 to n. I cubed 1 over n cubed 1 over n. And then this becomes 1 over n to the 4th. And anything without an I can actually bring out in front. So n to the 4th, I equals 1 to n of I cubed. At this point, what you have to do is you have to do this summation using a formula for the sum of I cubed. So that's either commonly given. It's kind of annoying to derive. Not annoying to derive. It's not too hard to derive, but like it would be annoying to keep deriving it. So in this case, I'll give you the summation. For a cube, sum of cubes, I think it is, I don't want to make a mistake on the derivation of this. It is n squared times n plus 1 squared over 4. Okay, so when I plug this into so that's what this is equal to. So if I do 1 over n to the 4th, we're gonna plug that into there. So I'm gonna get 1 over n to the 4th times n squared, n plus 1 quantity squared over 4. Okay, and this is gonna cancel with 2 of these. So I'm going to have 1/4 n plus 1 squared over n squared. And now I'm going to take the limit as n goes to infinity. As I take an infinite number of rectangles of this of 1/4. I can bring the 1/4 out because anything that doesn't depend on n I can bring out. So it's going to be n plus 1 squared over n squared. This part, if you want to do this summation, you could really do this as 1/4 times n squared plus 2n plus 1 over n squared. Right, and so I can change this to n squared plus 2n plus 1. And if you remember our rules, sometimes I think, well, as n goes to infinity, these two terms are going to dominate. So this is going to be 1. You could also use L'Hopital's rule, and you'll find that this limit is equal to 1. Or you could divide by n squared, numerator and denominator by n squared, and you'll also find this limit is equal to 1. So the answer is 1/4, because it's 1/4 times 1. Okay, so for 7, we're going to do kind of the same thing. The width of each rectangle is the width of my interval, which is 4 divided by the number of rectangles n. Okay, the height of each rectangle is going to start at -1 plus I times delta x. That's what I'm going to want to do. That's the height of each rectangle. And in this case, delta x is 4 over n, so that's f of -1 plus I times 4 over n. And then I plug that into here because this is my height, right? So we're going to do 3 times -1 plus I 4 over n plus minus 1. So these are the heights of each of my rectangle. These are the widths, and then I'm simply going to sum from I equals 1 to the total number of rectangles. The height of each rectangle, which is 3 times -1 plus I times 4 over n, minus 1. All of that multiplied by 4 over n. So now we got to do a little bit of distributing. This would be negative 3 plus 12 over n, and then minus 1. So this is going to be the sum from I equals 1 to n. 12 over n. Oh, where'd the I go? This would be 12i. Minus, sorry, this is negative 3 minus 1 minus 4. Okay. And so I'm going to break this into two sums. A sum with an I in it and a sum without an I in it. So I can do that. 12 over ni minus the sum from I equals 1 to n of 4. Oh, I forgot my 4 over n here. Wait. Yeah, 4 over n here. Okay, and so I can bring out anything that doesn't have an I in it. So this is going to be 48 over n squared, sum from n equals 1 to n. Oh, I equals 1 to n. Sorry, I'm making all kinds of silly mistakes. Let me clean this up a little bit so you guys can see that a little bit better. This part was this one. This would be the 12 over n times I times 4 over n, right? And so this would be 48 over n squared, sum from I equals 1 to n of I, minus 16 over n, sum over I equals 1 to n of 1. Now this is just the sum of a bunch of 1s, right? Because I put the 16 over n, I pulled it out. What's left inside is 1. An n sum of 1, this is equal to n, right? And then this sum is equal to n. This one, there's a rule for the sum of n terms. It's n times n plus 1 divided by 2. So this sum ends up being 48 over n squared times n plus 1 divided by 2 minus 16 over n times n. That cancels. Should have been 16. I feel like 16 is a little bit high. Oh, no, I think that's okay. Let's see what the answer we get in the end is. Okay, so this becomes, oh, this is over 2, sorry. And so this becomes 24 n. I'm going to distribute the n. It's going to be n squared plus n over n squared minus 16. And if I take the limit as n goes to infinity, this goes to 1 because I have an n squared over n squared. So this ends up being 24 minus 16. That's equal to 8. Okay. Now, this is a kind of tedious way to perform an integral. Like, we're going to use antiderivatives, ultimately. That's the key part of we're doing this. But this is kind of like showing you as the limit of the definition of a limit for the, definition of the derivative as a limit. Yes, it is tedious to do it by hand and by the definition. It's good to know it conceptually as to what you're actually doing with the summation. But in practice, what you're going to do is a lot of antiderivatives when you're doing integrals. Okay, so let's take a look at this one here. So here we're doing the integral from 0 to 1 of 3x cubed minus 4x squared. Again, the width of each rectangle is going to be the width of the interval, which is 1 minus 0 divided by n. That's 1 over n. And then the height of each rectangle is I start at 0 and I add in I times delta x. Like I'm scooting over in the x point. And that's because I'm using a right-hand sum. That's f of I times x, which is just I times 1 over n. Which is, if I plug in I times 1 over n, I'm going to get 3 times I times 1 over n cubed minus 4 times I times 1 over n squared. So this is the height and this is the width of my rectangle. So then I'm doing a sum from from I equals 1 to n of all of this. Actually, let's just go ahead and distribute the cubes. So this is 3i cubed 1 over n cubed minus 4i squared 1 over n squared. Right, so it's going to be 3i cubed 1 over n cubed minus 4i squared 1 over n squared. And then I'm going to multiply this by 1 over n. So this is going to be sum from I equals 1 to n. 3 over n to the fourth, right? Because I'm going to have this 1 over n times I cubed minus 4 over n cubed I squared. And so I'm going to break these into two different sums and factor out anything that doesn't have an I in it. So it's 3 over n to the fourth sum from I equals 1 to n I cubed minus 4 over n cubed sum from I equals 1 to n of I squared. And so now we're going to use our tricks for the sum. This one here is equal to n squared n plus 1 quantity squared over 4. And this one's equal to n plus 1 2n plus 1 over 6. Now these are just formulas that are just generally given to you. There are ways to derive them, not typically covered in calculus, unless your teacher just wants you to know it. But there are ways to derive these formulas for these summations, and that's what we're going to use. So now my sum becomes 3n squared n plus 1 squared over 4n to the fourth minus 4 times n plus 1 2n plus 1 over 6n cubed. And I'm going to cancel this to become squared and cancel one of these to become squared. And so this becomes, pulling out the constant in front, it's going to be 3/4 n plus 1 squared over n squared minus 4 over 6 is really 2 over 3 n plus 1 2n plus 1 over n squared. Now, if you think about the expansion of these, this is how I do it. Remember, I want to look at the dominant term. These are going to be polynomials. The dominant term here is going to be n squared. The rest of the terms are going to sort of, as n goes to infinity, are going to be smaller. There's going to be a 2n term and a 1 here, but that's going to vanish. So this is really going to go like n squared, and this is really going to go like 2n squared, right? And so when I take the limit as n goes to infinity, this is just 1. So this is 3/4. This limit ends up being 2 minus 2/3 times 2, because those are the dominant terms on the numerator and denominator. The n squareds will cancel, which is what should always happen when you're doing the definition. They should always cancel like that, or at least the numerator and denominator should be the same degree. And so this is 3/4 minus 4/3, and what's that? 9 minus 16, that's minus 7 over 12. Okay. So in these problems, we're going to convert the infinite sums into an integral expression. So we're kind of going the other direction. Before we had taken an integral and we want to convert it to the sum to compute the integral. And here we're going to try to like sort of pattern match it. Now there's actually a lot of different answers that would get you the same thing. But a lot of these times there's like a sort of a standard way to look at them. So again, what you want to try to do is you want to parse it into something that's like some function of, like, these are the heights and these are the widths. You want to break it down into the height of the rectangle and the width of the rectangle. So in this case, my width of my rectangle, delta x, is going to be 3 over n. So that's kind of like my b minus a over n, if you will. So I know my interval width is 3. If I think about it as like each, like the individual rectangle, like the whole region is 3, and I divide it by n rectangles. That's one physical interpretation we could do for this delta x. So we know the span of it is 3 over n, and then we know that my f of x has to be the starting point plus like multiples of delta x, like that, right? That's how I start at some point, and I keep adding over and over to get to each adjacent rectangle to find the height. So this, my f of x in this case, would then be 1 plus x. Oh, actually just equal to x. Sorry. Because what I'm doing is I'm doing f of some function, and as long as I identify that this is a and this is my delta x. Oh, there should be an I in here in this problem. I'll fix that. Yeah, these are missing an I in them. Right there. And I just copied that over incorrectly. So my f of x is just equal to this. So this integral ends up being x dx, and we're going from 1 to 4. Because I'm starting at 1 here, and my width is 3, so I'm going 1 to 4. And you can do this by doing it backwards. If I did it backwards of setting up this integral, you'll find that this is definitely the case here. So this would be my answer. So a similar thing is happening here, right? My delta x is equal to 1 over n. Okay, and then what I'm doing is I'm doing some sort of f of x. And you definitely think, well, it's definitely square root, but it's not simply square root of x. This is actually a little bit tricky. Because really, this is 2 over n times I. Remember, this part here, the way I think about it is I need it to be I times delta x, right? That's kind of the base idea of the Riemann sum integral, is it's f of a starting point plus I times delta x, all of this times delta x. So it's actually not good to call delta x 1 over n in this case, because really, if I wanted to pattern match this, I really should say delta x is 2 over n. Okay? And that would fit the inside very well. But the outside's not 2 over n, so how do I reconcile that? Well, I convert this to saying, well, this is 2 over n times 1/2. That's how I can modify this to match. See that? And so then we have this, so then we make this sum 1/2 the limit as n goes to infinity. The sum from I equals 1 to n, 2 over n, square root of 2 over ni. And so now I have my delta x, and now I have my delta x is 2 over n. So my interval width is 2, and in this case, technically, I'm starting at 0. So this would be the integral from 0 to 2, square root of x dx, and then I gotta have this 1/2 that I handled out right out here. Okay. Here's kind of a similar thing. The inside here is my delta x right here. Delta x is equal to pi over n. I'm going to start at 1, but I'm sort of doing negative. So this is a little bit tricky. My delta x is like negative. So you could say, you could think of it as I'm doing the integral backwards. So my delta x is negative pi over n. That would like make it, go correctly. Negative pi over n. But this is not equal to delta x. I need to put a minus sign here to make this match. And thus I need another minus sign out here to counteract this minus sign. So then my f of x can now match. It's just simply equal to sine squared of x. And the inside, the argument is my a plus I times delta x, right? And so I have my delta x, I have my I, and so my a is 1. So I'm starting at 1. What's my interval width? My interval width is negative pi over n, or negative pi. So I'm gonna go down pi. So it's gonna be 1 minus pi, and then sine squared of x dx. Okay.